Good morning all of you. In last video, some videos we discussed about the 2-3 gears. We discussed about the 2-3 gears. So in that we discussed about the some derivations regarding the distance between the center distance between the two gears shaft, two gear shaft. Also we discussed some numericals. We discussed some terminology of that particular gears of spur gears, and again that terminology is slightly modified in that particular helical gears, in helical gears, spiral gears or bevel gears, by consideration of that inclination of the tooth to the shaft axis. And we discussed some numericals based on this particular terminology, and we solved these numericals. We discussed about some interference of that particular interference that occur in gear, in these 2-3 gear interference, undercutting of in these 2-3 gears. We discussed these terms. We solved some numericals based on this all these particular points on particular topics, and now we move toward the another topic as a gear train. So this gear train is nothing but a collection. This gear train is nothing but a collection of gears. There is a collection of two or more gears. Gear train is nothing but a collection of two or more gears. Due to collection of these two or more gears, we transfer power from one shaft to the other. So we can define this gear train as it is a collection of two or more gears, so that we can transmit power from one shaft to the another shaft. So this gear train may use spur gears, helical gears, spiral gears or bevel gears. May use this type of the gears, and these gear trains are generally classified as a simple train, compound train of gears, reverted train of gears, and epicyclic train of gears. These are generally classified in four types. Simple train, compound train, reverted type, and epicyclic type. So we move towards this simple train of gear. So in this simple train of gears, this ratio in simple train of gear, only one gear. There is only one gear on one shaft. Each shaft. There is only one gear on each shaft. Only one gear on each shaft. Both gears are meshing with each other. And they transmit power from one shaft to the another shaft. So suppose we consider this diagram. So first gear is mounted on one shaft. Second gear is mounted on another shaft. And on this shaft of this second gear and shaft of first gear, there is only one gear on that particular shaft, and two gears are meshing with each other and transmit power from one shaft to the another shaft. And now here, first will be the driver and second will be the follower. First given some power, input power, some have some input power, and this input power transmitted to the second gear. Now here this direction of this particular first driver, suppose it is a clockwise. Direction of this first wheel, it is a clockwise. Then obviously the direction of the second wheel is a anti-clockwise. So in simple gear train, that direction, if these are externally meshed, then we can say that direction of this, both the gears are opposite to each other in simple gear train. And we can write this ratio of this angular velocity omega 2 by omega 1 of that particular wheels is equal to T1 by T2. So this ratio of speed of the driven gear to the speed of the driver gear, this ratio of speed of driven gear to the driver gear is nothing but a train value. So this ratio of speed of driven gear to the driver gear, it is nothing but a train value. And if you consider that ratio of speed of driver wheel to the speed of the driven wheel, then it is called as a speed value or velocity ratio. then it is called as a speed value or velocity ratio, VR, generally denoted as a VR, velocity ratio. So velocity ratio is nothing but a ratio of speed of the driver wheel to the ratio to the speed of the driven wheel, driver wheel to the driven wheel. This is called as a velocity ratio. This is called velocity ratio. Now in this second diagram, if you look at the second diagram, there are three shafts. First shaft, second shaft, and third shaft. On each shaft, one gear wheel is mounted. One more gear wheel is mounted. First, second, and third. Now, first gear wheel is come in contact externally, mesh with the second wheel. Second wheel is mesh with the third wheel externally. And if you look at this construction, we can in this construction, first wheel, suppose first wheel is the driver rotating in clockwise direction. It give power to the second wheel. Now second wheel give power to the third wheel. Now first wheel rotate in the clockwise direction, second wheel rotate now in anti-clockwise direction, and third wheel now rotate in clockwise direction. So in this case, in this case B, direction of rotation of first wheel and direction of rotation of third wheel are the same. Direction of rotation of first wheel and direction of rotation of third wheel are the same. And second wheel doesn't contribute in the velocity ratio. Second wheel doesn't contribute in the velocity ratio. So second wheel in such type of the construction, this second wheel is considered as an idler gear. It doesn't contribute in the velocity ratio of this particular gear drive. So this second wheel is considered as an idler wheel. And we can write for this case. Like this. Train value is nothing but a ratio of the driver wheel to the driven wheel. So train value is nothing but the ratio of the driven wheel to the driver wheel. Ratio of driven wheel to driver wheel. So nth gear is the last gear. It is a driven wheel ratio speed divided by speed of the driver gear, first gear. Driver of that particular gear drive is the first gear. N by N1. So these are equal to this like this. T1 by T2 into T2 by T3 into T3 by T4 like that, up to Tn minus 1 divided by Tn. So these T2, these terms, second power gear, second gear, third gear, and this Tn minus 1, these are the intermediate, these are the idler gears. These are removed, and only remaining term is a T1 by Tn. So this is the train value, and speed ratio is opposite to this. Speed ratio is opposite to this. So not speed value or velocity ratio. Speed value or velocity ratio is opposite to this. So this is the train value. Ratio of speed of the driven to the driver. Ratio of speed of the driven wheel to the driver wheel. So this we can write like this. Now we can write velocity ratio or speed ratio. Like this. So speed ratio here I write here as a. Now speed ratio is the ratio of speed of the driver wheel to the speed of the driven wheel. Ratio of speed of the driver wheel to the ratio of speed of the driven wheel. So we can write like this. Now we go through some numericals. So this is the one numerical is given. Here one numerical is given. A simple gear train comprises 3 gears. each fixed on the separate shaft. The shafts are parallel. The gear 1 is the driver, gear 3 is the driven gear. Gear 1 is running at 1000 rpm. Number of teeth on first, second and third are the 40, 50 and 80 respectively. Determine the speed ratio of the gear train, speed of the rotation of the driven wheel and its direction. So they asked to find out the speed ratio and also asked to find out the speed of rotation of the driven wheel and its direction. Speed of particular driven wheel and its direction. So we have this speed ratio is equal to, velocity ratio, and the speed ratio is nothing but the speed of the driver wheel, to the speed of the driven wheel, and it is a reciprocal of this particular. If you write in terms of the teeth, it is a reciprocal one. So number of teeth on the driven divided by number of teeth on the driver. So it is a just reciprocal of this particular term, speed ratio. Number of teeth on the driven and number of teeth on the driver. So for third gear, for speed ratio we can find out the number of teeth on this third gear is 80 and for first gear is 40. So this is 80 divided by 40 is equal to 2. So speed ratio is nothing but 2. Now speed of the driven wheel is the, we can find out by using this formula. Speed ratio is equal to speed of the driver divided by speed of the driven. So speed of the driven is nothing but speed of driver divided by speed ratio. So speed of the driver is given as 1000. Speed of the driver is given as 1000. 1000 rpm is given. So put this 1000 divided by 2 is equal to 800 rpm. So this such type of the simple numericals, in which only if you understand this speed ratio term, we can write the speed ratio term in terms of the speed of the particular gear wheels and also in terms of the ratio of number of teeth of that particular gear wheels. So by using this we can simplify these numericals. So we go through the next example. So in this example, they are asking to determine the number of teeth and pitch for the two 3 gear wheels to transmit a velocity ratio of 5 to 1. So velocity ratio is given as 5 to 1 between two parallel shafts by simple gear train. So simple gear train is given, velocity ratio is given 5 to 1, and they asked to find out the number of teeth and pitch for the two 3 gear wheels. Center distance between this parallel shaft is 865 approximately. Drive must satisfy the following requirements: standard pitch in terms of module, in terms of mm must be chosen from this data. So module should be chosen from this data only, and the number of teeth as small as possible. Second condition is given as first condition is given, module should be chosen from this given data, and second condition is given as the number of teeth as small as possible. So with this condition we have to find out the number of teeth for the gear drive, for the simple gear train. So we have just formula C is equal to, center distance C is equal to d1 plus d2 by 2. Center distance between the two shafts or two gear wheels we can find out by addition of the pitch circle radius of the both the gears. So d1 r1 plus r2, but if you write in terms of the diameter, it will be d1 plus d2 divided by 2. So this d1 we can write as a mt1 in terms of the module, and in terms of 2 we can write as a mt1. d2 we can write as mt2 divided by 2. Now velocity ratio is given, and there are only two gears. So we can write as a t2 by t1 is equal to velocity ratio is equal to 5. It is given. Now from this equation we can calculate t2 in terms of t1. T2 in terms of T1 as a 5 T1. Now put this T2 value into this center distance equation. Center distance is given approximately 865. So put this value 865 is equal to mt1 plus 5 mt1 divided by 2. So we get this equation 865 is equal to 3 mt1 is equal to 3 mt1. So mt1 we can get is equal to 288.33. Now we simplify. Now in this equation we put value of m. We put value of m from this given data. We put value of m from this given data, and we again calculate. That particular teeth value. We calculate the teeth value, and again we calculate the center distance. Again we calculate center distance in between the two gears. Center distance in between the two gears. So here first we select that. First we select this m value. Select this m value. So minimum number of teeth for the pressure angle 20 degree is 18. 20 degree is 18. So with T1 is equal to 18. With T1 is equal to 18. So for pressure angle 20 degree, that minimum number of teeth is 18. So we consider T1 is equal to 18. Put this T1 is equal to 18 into this equation. So this value of module comes as a 16.018. But in the given data, module is given as a 16. Module is available as a 16 model, 16 mm model. So so this is approximately considered as a select model as a 16 mm. Now with this consideration of 16 mm module, we put again into this equation, previous equation, T1 is equal to, again T1 is equal to 288 divided by m, 288 divided by m, now 16, so it becomes as a 18.02. So this again approximated as a 18, again it is approximated as 18. So T2 in terms of T1 is a 5 T1, so T2 now comes as a 90 teeth. And now we can calculate center distance as a mt1 plus mt2 divided by 2. So m now 16 and T1 and T2 now becomes as a 18 and 90. So it becomes as a 864 millimeter. So previously that center distance we consider as 865, and new center distance due to this some approximation, or by considering this whole amount of teeth and considering this whole amount of module from data, this again changes as a 864, and variation in between this center distance we can calculate it like this: final minus initial divided by initial into 100. So final is 864, initial is 865 divided by initial is 865. Here should be 865 into 100. So it becomes as a minus 0.1157%. So variation of center distance is within acceptable limit. So this limit is also given. This percentage limit is also given in numerical. This percentage of given also in the numerical. So here in this numerical also given that percentage of variation is should not be varying more than 1%. So it is given in numerical. So it is a given data. So it is within acceptable limit. So these are some numericals on the simple gear train. So in this numerical, first we consider number of teeth. 18. From this 18 number of teeth we find out the m value. Now from given data, this m value it is not available in given data. So in given data, whatever that value is very near to this, we consider that one. So we consider that one 16 millimeter. Again with this 16 millimeter model value, again T1 changes. Again T1 changes as a 18.02. Again it is teeth should be whole number. so it should be 18. It should be 18. So T2 will now becomes 90T. And due to this approximation, 16.08 now considered as 16, 18.02 considered as 18. Due to this approximation or whole consideration of whole numbers, this C exact again changes. Now it becomes like this. By putting these values, now this becomes like this. So center distance now again changes slightly, and we can find out the percentage variation of the center distance, and that will appears as a 0.1157. So here by printing mistake it is 864, it is 865, it is 8 should be 865, and that will become as a 0.1157, and it is also within acceptable limit. It is also in the acceptable limit.